Welcome to Alchemical Science. I'm Jordan, a self-taught farmer, electrical engineer and physicist who conducts open source research in the areas of unified field theory, soil science, plant biology, radiant energy, neuroscience and the energy systems of the human body. I'm also a practicing alchemist, and so I try to employ a research methodology that's informed and directed by the hypothesis that there is a universal pattern that can be observed in all aspects of the natural world. We just need to look for it. So today we're going to be looking at setting up biofeedback algorithms using the open source software Brainbay. And to do it, I'm just using my trusty EXG pill here, which is a biofeedback amplifier, but you can use any number of designs. You'll see in Brainbay in a moment that there is a lot of different ones that are compatible with it. So check through, see what suits your needs and your price range. The EXG pill is very cheap. It's just one channel at the moment, although you could probably set them up to do multiple. I haven't tried yet. But anyway, we're just going to jump straight in. I'll start recording the computer screen so we can see the Brainbay software. Alright, so first of all, you'll need to jump on the Brainbay website and go over to the downloads page and download the latest version. So you can see it's only available for Windows. If you've got a Mac like I do, you can install Windows using Boot Camp, and you can just Google how to do that. It's already a function that is on Mac that you just need to get a copy of Windows and install it. But either way, you'll need Windows. I found that trying to emulate it just on Mac OS itself doesn't really work very well. You have a bit of trouble reading the COM ports and being able to use this properly with Brainbay, so you're best off with a native Windows installation. So yeah, you'll need to download and install that, and then we just can jump over. This is what it'll look like when you open up the software, and you can see there's a few sample files here, and if you go into load designs, there's a bunch of other ones here that you can just play around with to kind of get a bit of a lay of the land. But otherwise, we just want to go over to New Design, and so you'll get this blank workspace here. So I think Brainbay has a lot of different applications for a lot of different people, like just for home experimenters. It's obviously free and open source, but also for schools, for teachers, for students, universities. Being able to set up your own experiments this easily and with such a low cost is really incredible. So thanks to the Brainbay creators for giving us this open source software. But jumping in on how to use it, so we can see insert element is the main menu we're going to be using here, and you've got sources, processing, target, and others, which are just a little bit some fun stuff like games, so you can make some mind-controlled games and things like that. There's amazing applications here for just having fun. But first of all, we're going to set up a sample algorithm which would be designed to read EEG wavebands at this stage. So that's the 1 to 30 hertz range, and obviously depending on the biofeedback signal you're looking to capture, just go and look up what waveband that you should be tuning into, and then you can use your filters to go and set up your own algorithm to be able to use it for that application. But for now, we'll just set up this sample one to be able to read the standard EEG signals. So I've got my EXG pill plugged in here, and I'm just going into source and then biosignal, EEG amplifier. And you can see there's all these different ones that you can use here. I use this particular setting with the EXG pill. It works with it. There's a sketch available on Upside Down Labs GitHub page that'll allow your EXG pill to work with this one here. So I'm going to click on that, and then we need to select the COM port it's connected to. In this case, it's COM6 for me. If you're using an Arduino based one, then you can jump into the Arduino IDE and just check what the COM port is of the connected Arduino down in the bottom right. But yeah, otherwise, just look in your Windows settings to find out which COM port your amplifier is attached to, and then we want to connect. And you can see the connection box is ticked there to tell us that that's correct. And that's our source here. You can see it's got all these channels, and it can have more, but we're just going to be using channel 1. So next, we're going to go into the processing menu, and we're going to set up some filters for the different wave bands that we want to show on the oscilloscope. So I'll just move this filter over here, and it's going to be connected to channel 1 on the oscilloscope, so we just drag from that dot over to the filter dot. This is all very easy drag and drop stuff. And then we're going to right click on the filter so that we get this little setting window popping up. So because we're doing EEG, generally we want to separate the displays on our oscilloscope into the delta band, the theta band, alpha, beta, and gamma if you're tracking that. So for now we're going to call this one delta, and that's going to be 1 to 4 Hertz. And then we're going to set this as a bandpass Butterworth, which will make sure that only the signals in this range come through, and just hit apply. And then we can rename our filter there just by double left clicking on there, and we could call that delta, for example. So a 1 to 4 Hertz range. And then I won't make all of these up, but we'll make one more up. So another filter. And just while I'm in here, for example, if you ever needed to filter out electrical noise, because often the electrical grid, the 50 or 60 Hertz, can really get in the way of your signals if you're processing in that band. So just a quick note here is you could do a 50 Hertz filter, and I won't need this for what I'm doing now, but you could do a 50 Hertz filter and set this from 49 to 51 Hertz, and then set this as a band stop Butterworth, and then that will stop any signals in that 49 to 51 Hertz band completely, and therefore filter out that electrical grid noise. And you'd obviously set that to 59, 61 if you were in a country where that was the primary frequency of your grid. So for now though, we don't actually need that, so we're going to call this our theta band instead, and we're going to set this from 5 to 8 Hertz, and then we're going to set that back to a bandpass Butterworth. Hit apply, and we're going to rename that one, oh sorry, not there, double click on it and rename that one theta here. So then we would connect that straight to our channel 1 as well, because we're only using a 1-channel device, and that's all there is to that. So obviously we'd make our delta, theta, our alpha, our beta, our high beta. So we could set those up just in the same way, so I won't go through that. But for now, I'll just move these down ever so slightly. And we'll go back to insert element, and we'll make something to display our filtered signals on. So we'll make an oscilloscope here, and it'll come up with some settings. So first of all, you can set the colors of, well actually there's only one there, so we'll actually come back to that. So we'll close that for now. Okay, so we'll drag that down here, we'll drag our oscilloscope element over here, and then just so we can receive our raw data from the EEG, we'll drag straight from channel 1 straight into channel 1 of the oscilloscope. And then we can right click on the little circle of that so we can rename this channel. So we'll call that raw, and then we can set the input range, and this will determine the scale of the display on the oscilloscope, but we will wait to do this until we actually see our signal, and then we'll rethink this. So we'll close that for now. So then we'll make our second oscilloscope display from delta. So one thing we can do with our oscilloscope now is just right click on it, and you'll see drawing styles and colors section here. You can change the background of the grid, etc. and the size of the drawing, and which is, you know, the thickness of the line of the wave, and then also change the color of the signals. And they're all kind of just red and dark red and stuff now, so it's a good idea to just change those straight away into all something a little bit different. So we'll do that. Then we can just close this again. You can also, there's one other option here that's interesting, group signals, and it'll just make all of the signals appear in their different colors on the same oscilloscope. So that's actually quite useful for some readings and some comparisons. But for now, we'll just leave them as separate oscilloscopes. So another very useful element that has a lot of applications is the FFT spectrum analyzer. So we'll put one of these in here. So this is it down here, just in small, but we'll, first of all, bring that over here. We'll make that quite a bit bigger. So you can see we've got the 1 to 40 Hertz range here by default. So we drag this one down here. We again can use our channel 1 input here, or we can use any of our filters to filter the input. So then if we right click on the FFT window, we can go import colors. And then Brainbay just has some preset ones here, so I'll just use this one here, and you can see that that's set some colors here for my graph from the 1 to 40 Hertz. So I'll also make the background color black, just so I can see everything a little better there. It's set on a bar graph here by default, but you can experiment with these, and there's a lot of different displays that you can get your data in, but we'll just leave it as a bar graph for simplistic values here. And we can set the range here, so, you know, in our case we'd be doing 1 to 30 if we're just not including the gamma range. So we have our 1 to 30 there, and we can adjust the gain and the calculated interval here, and you'll play around with those once you get your signal. So otherwise, the only other one I'm going to show you for now is there is a few different processing options. So you can see that if you're looking for a particular purpose, it's probably here. There's a lot of different options on processing your data. But for example, you know, we've got these 3 outputs on the FFT, the average, the power, and the peak. So if we wanted to know what the average peak frequency, or sorry, the peak frequency at any given time is, or the average peak frequency over a time is, then we could insert just a simple counter display and just go display value, no counting there, and then close that. We get this little counter window there, and you can just drag that down here, and then you can connect your average or your peak, your power to the in, and then it's going to give you that value in that little window. So that's a handy little just an extra way to kind of process the data. You can see that all of these have inputs and outputs, so if it has an output, as long as you put an appropriate element to be able to process that data. And you can see that there's a lot of different ones here, and same with a lot of different targets. You can write to a file, or you can use it to control sound within certain frequency ranges, and yeah, a lot of different interesting stuff. But at any rate, for this, you could also, for example, if you're using FFT for tracking a meditation session, you can make a graph with an oscilloscope of the power amplitude output at any given time of the FFT signal. So as the signal's coming in over the session, you can track the amplitude in the different wave bands, which has some use for yeah, tracking your own meditation and even just different states of mind and etc. So that's the basics there, really. We'll try and just get a signal now on our EXG pill, so we'll just make sure that that's connected there, and I'll quickly hook up the electrodes, and then we'll see if we can get a signal reading and try and tune these outputs. Alright, so it turns out I've run out of EEG electrodes, so I won't be able to give you a proper example here, but you'll be able to see what's going on. So I've opened up this new sketch instead, which is just a complete version of what I was showing before. So you can see the source, the filters here still, the oscilloscope here with all its channels, the FFT, and then I've also added a power amplification output from the FFT here in another oscilloscope graph, just for another purpose, but we'll ignore that for now. So yeah, you can see they're all coming from this one channel again, and we've got our oscilloscope here and our frequency spectrum graph here, just set up how they are in this particular design. So because they're not actually connected to anything, but the device is connected, I should be able to just hit play, yep, and get a bit of a messy wave there, because you always get a spike when the electrodes aren't connected. You'll get a quick spike there and then a quick reduction down to nothing again. But this allows us to just have a look at what's happening here. So the main thing to note here is that you need to tune these oscilloscope readings to display the wave in some way that's feasible. So obviously these are quite messy waves because everything's just spiking here, but within the reading that I was using this for, which was just for standard EEG for a meditation session, I've configured the voltage ranges here to display the waveforms how I want in this graph, and you can see that they'll come out of their graphs and overlap. And if your graph's getting too messy, you can always click that group signal checkbox in the oscilloscope settings, as I showed before, and then it'll group all of these together and just show them in one. But otherwise, yeah, you can see I've configured my gamma band from 13.4 to negative 13.4, and well, it looks like I've done that with nearly all of them, and except my theta 16.42 and my delta 328.41, because those delta waves are massive, especially if you're getting them into coherence with meditation. They can take up a lot of space. So that's just setting those ranges there. And then of course the way you do that is just to go to your oscilloscope and click on each channel, right click on the dot, and then you can set that range there. So, you know, if I needed to make the waveform larger, I would you know, maybe make this one you know, negative 10 and to 10, and if I wanted to make the waveform smaller, I might make it negative 160 to 160. So you can configure it in that way to tune in to see those signals. And same thing with the frequency, the FFT graph. If you just right click on there, aside from setting the range, you can also set the gain on each axis, each axis, and the overall gain as well, which will just, you know, if you're finding that it's just one big block of color, then bring your gain down a little, and if you're finding that you're barely getting a signal, bring your gain up a little, and in that way you'll be able to get a clear signal. So that's about all I'm going to go through on Brainbay today. I mean, there's a lot of options there and I'm still exploring them, but I found that the things I've showed in this video really covers all the basics on, you know, biofeedback signals, all the signals of the human body, you know, the experimental stuff I've been showing with plants, and, you know, anything else you're doing in that extremely low frequency band where you need high amplification. Yeah, this works really great, and you can design all your own experiments.